National Electrical Code Section 450.14 necessitates a disconnecting means for a transformer. This requirement implies that a single disconnecting means is adequate to isolate the transformer, ensuring it is de-energized from all power sources. When a transformer is supplied by multiple medium voltage breakers, each breaker can independently serve as a disconnecting means, isolating the transformer from its respective source. However, the presence of multiple feeders, each with its own disconnect, doesn't negate the necessity for a single, dedicated disconnecting means, as stipulated by NEC Section 450.14. For safety and adherence to lockout-tagout protocols, it remains imperative to lock out all medium voltage breakers before undertaking any maintenance or servicing on the transformer. This comprehensive lockout procedure guarantees complete isolation and de-energization of the transformer, mitigating any potential electrical hazards during work activities. In conclusion, while the implementation of multiple feeders, each equipped with its own disconnecting means, offers enhanced operational flexibility and system redundancy, NEC Section 450.14 specifically mandates a separate and distinct disconnecting means for the transformer itself. Therefore, even in scenarios where the transformer is fed from two or more medium voltage breakers, the installation of a dedicated disconnecting means remains a mandatory code requirement. It is crucial to ensure that the designated disconnecting means is clearly labeled for ease of identification and readily accessible to facilitate prompt and efficient operation. Employing a fuse disconnect or circuit breaker as the disconnecting means is highly recommended, as it provides supplementary protection against short circuits, thereby enhancing the overall safety and reliability of the electrical system. Furthermore, the selected disconnecting means must conform to all applicable requirements outlined in the National Electrical Safety Code, specifically those pertaining to outdoor installations, to ensure compliance with industry best practices and regulatory standards. Considering the practical implementation, the disconnecting means should be installed as close as possible to the transformer to minimize the length of unprotected conductors. This proximity reduces the risk of faults occurring between the disconnecting means and the transformer. The disconnecting means should be rated to interrupt the available fault current at its location. This ensures that it can safely clear any short circuits or ground faults that may occur within the transformer or its connected circuits. The disconnecting means must be suitable for the environmental conditions at the installation location. For outdoor installations, it must be weather resistant and protected from corrosion. Ensure that the disconnecting means is properly grounded to provide a low impedance path for fault currents to return to the source. This helps to protect personnel and equipment from electrical shock and damage. The location of the disconnecting means should be clearly marked with signage that is visible and easily understood. This helps to ensure that it can be quickly located in an emergency. Regularly inspect the disconnecting means to ensure that it is in good working condition. Look for any signs of damage, corrosion, or overheating. Test the operation of the disconnecting means periodically to ensure that it is functioning properly. This can be done by opening and closing the disconnect and verifying that it interrupts the power supply to the transformer. Maintain records of all inspections, tests, and maintenance performed on the disconnecting means. This helps to track its condition and identify any potential problems. When selecting a disconnecting means, consider the following factors. Firstly, the voltage and current rating of the transformer. Secondly, the available fault current at the installation location. Thirdly, the environmental conditions at the installation location. Fourthly, the applicable codes and standards. Fifthly, the ease of operation and maintenance. Sixthly, the cost. Typical disconnecting means include fuse disconnect switches and circuit breakers. Fuse disconnect switches provide overcurrent protection in addition to disconnecting means. Circuit breakers also provide overcurrent protection and can be remotely operated. Selecting the appropriate disconnecting means involves considering factors such as voltage, current, fault current, environmental conditions, and applicable codes, including the National Electrical Code and the National Electrical Safety Code. The disconnecting means should have a voltage rating equal to or greater than the system voltage. The current rating should be sufficient to handle the full load current of the transformer. The interrupting rating should be sufficient to interrupt the available fault current at the point of installation. The enclosure should be suitable for the environment in which it is installed. The disconnecting means should be readily accessible for operation and maintenance. It should be clearly labeled to indicate its purpose. Regular inspection and maintenance are essential to ensure reliable operation. Inspect the disconnecting means for any signs of damage or deterioration. Test the operation of the disconnecting means periodically. Keep the disconnecting means clean and free of debris. Repair or replace any damaged or worn parts. It's worth noting that the specific requirements for disconnecting means can vary based on local codes and regulations, so consulting with a qualified electrical inspector or engineer is advisable to ensure compliance. The intent of NEC Section 450.14 is to provide a readily accessible means to energize the transformer for maintenance, repair, or in case of an emergency. The disconnecting means must be installed at a location that is easily accessible to qualified personnel. The disconnecting means must be capable of being locked in the open position to prevent accidental re-energization. The disconnecting means must be clearly labeled to identify the equipment it disconnects. The disconnecting means must be suitable for the voltage and current it will be subjected to. The disconnecting means must be installed in accordance with the manufacturer's instructions. When multiple disconnecting means are used, they must be arranged so that all sources of power to the transformer can be disconnected simultaneously. This may require the use of a group-operated disconnect switch. The disconnecting means should be located as close as practicable to the transformer. This minimizes the length of unprotected conductors. The disconnecting means should be located in a safe and accessible location. It should not be located in a hazardous location or where it could be easily damaged. The disconnecting means should be protected from the weather. If the disconnecting means is located outdoors, it should be installed in a weatherproof enclosure. The disconnecting means should be properly grounded. This helps to protect personnel from electrical shock. The disconnecting means should be inspected and maintained regularly. This helps to ensure that it is in good working condition. Keep accurate records of all inspections and maintenance. This helps to track the condition of the equipment. Consider the following aspects when selecting the location for the disconnecting means. Firstly, accessibility for authorized personnel. Secondly, proximity to the transformer. Thirdly, environmental conditions. Fourthly, safety considerations. Fifthly, applicable codes and standards. For a 750 kV amps oil-filled pub-mount transformer, additional considerations apply due to its size and potential hazards associated with oil-filled equipment. Oil-filled transformers require special handling and safety precautions due to the potential for oil leaks or fires. The disconnecting means should be located in a safe location away from potential hazards such as flammable materials or pedestrian traffic. The disconnecting means should be readily accessible for operation and maintenance, even in adverse weather conditions. The disconnecting means should be sized appropriately for the transformer's voltage, current, and fault current ratings. Consider using a fused disconnect switch or circuit breaker that provides both overcurrent protection and a disconnecting means. Ensure that the disconnecting means is properly labeled and identified. Install warning signs indicating the presence of a high voltage transformer and the location of the disconnecting means. Develop and implement a lockout tagout procedure to ensure that the transformer is de-energized and isolated before any maintenance or repair work is performed. Train personnel on the proper operation and maintenance of the disconnecting means and the associated safety procedures. Regular inspections and maintenance are essential to ensure the safe and reliable operation of the transformer and its disconnecting means. The National Electrical Code provides comprehensive guidelines for the installation and maintenance of electrical equipment, including transformers and disconnecting means. Consult the NEC and other applicable standards to ensure compliance with all relevant requirements. It is important to consult with a qualified electrical engineer or contractor to determine the appropriate disconnecting means and installation requirements for a specific application. The selection and installation of a disconnecting means for a transformer is a critical safety consideration. Proper planning, design, and installation are essential to ensure the safe and reliable operation of the electrical system. Additional consideration should be made for a 15 kV source. Disconnecting means must be rated for 15 kV or higher. Use appropriate personal protective equipment when working with high voltage equipment. Ensure that all personnel are properly trained on the hazards of high voltage electricity. Follow all applicable safety procedures. A 15 kV system presents a higher risk of electrical shock and arc flash. Therefore, it is important to take extra precautions when working with this type of system. The disconnecting means should be located in a secure location to prevent unauthorized access. The disconnecting means should be interlocked with the transformer to prevent operation when the transformer is energized. The disconnecting means should be equipped with a visible break to verify that it is open. The disconnecting means should be tested regularly to ensure that it is functioning properly. The disconnecting means should be maintained in accordance with the manufacturer's instructions. The disconnecting means should be inspected regularly for any signs of damage or deterioration. Any damaged or deteriorated components should be replaced immediately. It is important to follow all applicable safety procedures when working with high voltage equipment. Failure to do so could result in serious injury or death. The interrupting rating of the disconnecting means must be sufficient to interrupt the maximum available fault current at its location. This is crucial for safety, as the disconnecting means with an inadequate interrupting rating could fail catastrophically during a fault, potentially causing an arc flash or other hazardous conditions. The available fault current can be determined through a fault current study, which should be conducted by a qualified electrical engineer. The disconnecting means should be selected and installed in accordance with the recommendations of the fault current study. For example, if the fault current study indicates that the available fault current at the disconnecting means location is 20,000 amps, then the disconnecting means must have an interrupting rating of at least 20,000 amps. The interrupting rating of the disconnecting means is typically marked on the equipment's nameplate. The interrupting rating is also sometimes referred to as the short circuit current rating or the withstand current rating. In addition to the interrupting rating, the disconnecting means should also have a suitable withstand rating. The withstand rating is the amount of current that the disconnecting means can withstand for a short period of time without being damaged. The withstand rating is typically higher than the interrupting rating. The withstand rating is important because it helps to protect the disconnecting means from damage during a fault. The disconnecting means should be selected and installed in accordance with all applicable codes and standards, including the National Electrical Code and the National Electrical Safety Code. These codes and standards provide detailed requirements for the selection, installation, and maintenance of electrical equipment, including disconnecting means. Compliance with these codes and standards is essential for ensuring the safety of personnel and property. The disconnecting means should be inspected and maintained regularly to ensure that it is in good working condition. Regular inspection should include a visual inspection of the equipment for any signs of damage or deterioration. The disconnecting means should also be tested periodically to verify that it is operating properly. Any damaged or deteriorated components should be replaced immediately. Proper selection, installation, and maintenance of the disconnecting means are crucial for ensuring the safety and reliability of the electrical system. The cost of the disconnecting means is also a consideration. However, the cost should not be the only factor considered. Safety and reliability should be the primary considerations. It is important to choose a disconnecting means that is suitable for the application and that will provide adequate protection for personnel and property. The disconnecting means should be installed in a location that is easily accessible for operation and maintenance. The disconnecting means should be located in a safe location where it will not be exposed to damage. The disconnecting means should be protected from the weather. The disconnecting means should be properly grounded. The disconnecting means should be clearly labeled. The disconnecting means should be inspected and maintained regularly. By following these guidelines, you can ensure that the disconnecting means is properly selected, installed, and maintained, and that it will provide adequate protection for personnel and property. Also consider the coordination of overcurrent protective devices. Coordination of overcurrent protective devices is essential for ensuring the selective tripping of circuit breakers or fuses in an electrical system. Selective tripping means that only the overcurrent device closest to the fault should trip, while upstream devices remain closed. This minimizes the extent of the outage and allows the rest of the system to continue operating. The disconnecting means should be coordinated with the other overcurrent protective devices in the system to ensure selective tripping. Coordination studies should be conducted by a qualified electrical engineer to determine the appropriate settings for the overcurrent protective devices. Coordination studies involve analyzing the time current characteristics of the overcurrent protective devices and selecting settings that will ensure selective tripping. The time current characteristic of an overcurrent protective device is a graph that shows the amount of time it takes for the device to trip for different levels of overcurrent. The coordination study should also consider the available fault current at different points in the system. The available fault current is the amount of current that would flow during a short circuit. The overcurrent protective devices must be able to interrupt the available fault current without being damaged. The coordination study should also consider the impact of motor starting currents on the overcurrent protective devices. Motor starting currents can be several times higher than the normal running current of the motor. The overcurrent protective devices must be able to withstand the motor starting current without tripping. Once the coordination study has been completed, the overcurrent protective devices should be set according to the recommendations of the study. The settings of the overcurrent protective devices should be documented and kept in a safe place. The overcurrent protective devices should be tested periodically to verify that they are operating properly. Coordination of overcurrent protective devices is an ongoing process. The coordination study should be reviewed and updated whenever there are changes to the electrical system. Changes to the electrical system can include adding new loads, replacing equipment, or changing the configuration of the system.